My friends, welcome to your ECE 240 practice session. Tonight I will be solving Peter Levine's Fall 2021 practice exam. I guess it wasn't a practice exam for the people at the time. However, this was a 24-hour take-home exam. It was right during the height of the coronavirus. So I imagine that if it was on Peter Levine's final during 2021, it will probably be the hardest thing you could see in the final, but we will see what Wilson has in store for us, for sure. All right, without further ado, let me begin. I would like to say that by all means watch this on 1.5 speed or double speed or whatever you're comfortable with, but I am going to pause for 5 seconds before I begin every problem, and I encourage you to read the problem and think about how you would solve the problem at the very least, or I'm going to be posting a PDF of this exam as well as the solutions I come up with. So if you want to print off a copy and solve it yourself before going through my solution, that would be probably very good practice. Okay, let me begin. The first problem comes in 4 parts. There's 2 parts on this page and 2 on the next page. I'll start with this one. So the first question involves a voltage source, a capacitor, and a resistor network. The question is, calculate the time constant tau and the -3 decibel frequency. I changed this from pole frequency, which I believe was done at the, in Levine's class. We did -3 dB frequency of the circuit below. So I'll give you 5 seconds to ponder the problem. 5, 4, 3, 2, 1. Okay. So this problem initially confused me a little bit because the time constant has to do with like a charging of a capacitor from a DC voltage, like an RC circuit, whereas the decibel frequency has to do with AC, sinusoids. What I believe is going on here is V in, you should treat it as DC to find the time constant, and then you should treat it as AC to find the -3 decibel frequency. So that's what I'm going to go with. So what do we have? We have that tau is equal to 1 over RC if we can express the circuit as a like an RC circuit. So let's try to do that. What I can say for sure is that the 5 kilo ohm and 15 kilo ohm are in series, so their effective resistance is 20 kilo ohms, and this together is in parallel with a 10 kilo ohm resistor. So I'm going to redraw, I guess, this circuit as, so we have plus minus V in, and then we've got one resistor here with resistance 6.67 kilo ohms, and then we've got a 20 microfarad capacitor, and we have another resistor up here. And then on this side, we also have a separate resistor coming back to the other side of our voltage source. This one has resistance 20 kilo ohms, and this one has resistance 25 kilo ohms. Now, I can tell you that when the voltage source turns on, if we're considering a DC transient, what will happen is the current will immediately flow in this loop according to Ohm's law. And then what happens in this loop will be independent of what happens in this loop. If there was a resistor here, let's say, that would not be the case. But what I can do is I can simplify this circuit further to say that, this looks like plus minus V in, and then we've got 6.67 kilo ohms, and then we've got 20 microfarads, and then we've got 20 kilo ohms. Then this looks a little bit more like the RC circuit that you're used to. We can combine these two resistances because they are now in series. Yeah, we can do that. And our resultant circuit will be simply plus minus V in, and then we've got ourselves a 20 microfarad capacitor, and then a 26.67 kilo ohm resistor. This is only for DC, I believe. No, that works equally well for AC. And then what we can say is that tau is equal to 1 over RC is equal to 1 over 26.67 kilo ohms times 20 microfarads, and that calculator time. Those of you who did this in your head, I'm very impressed with you. 26.67. Well, that should be 533.33, but nah, same difference. We're going to say that this is equal to 1 over 533 times 10 to the negative 6. And that the tau itself would have units of... Wait, hold on a minute. This is kilo ohms. Sorry, my bad. This should be 10 to the negative 3 in that case. And then has units of ohm farads, I guess. And then if we were to convert this, we would divide 1 by 533,000, then it would be, we get 1.87 times 10 to the negative 10 to the... Oh. It's not 533,000, it's 0.533. Oops. 1 divided by 0.533. That should give you 1.876 ohm, negative 1 farad, negative 1. Okay, that's your time constant. Now, if you want to find the negative 3 dB frequency, you can still use this circuit. However, and I will do this on a separate blank piece of paper. I will probably have to redraw it out in this case. That's okay. What we have is our minus Vn, and then we have our 20 microfarad capacitor, and then we have 26.67 kilo ohm resistor. And so we know that if Vin becomes an AC, then we can find the reactance or complex impedance of the capacitor. So we can redraw this as Vin, and then this will have resistance of 1 by j omega c, which, well, I guess I can plug it in. So it's negative j 1 by 20 times 10 to the negative 6 W, we'll say. And then this one is just as usual. It has Z is equal to, well, 26.67 kilo ohms. Easy. So the question becomes, when is, at the 3 dB frequency, when is V out, and I will bring you back to the original circuit here. V out was only the impedance across, only the voltage drop across the 20 kilo ohm resistor here, not the 6.67 kilo ohm that we've got connected here. So, when is V out equal to 1 over root 2 times V in? That's our question. So, you can see how, hopefully, if this we could divide this into a 6.67 kilo ohm and the 20 kilo ohm that we're worried about for the voltage drop. Since they're in series, we can just do voltage division. So what we can say is that V out is equal to, and we'll call this maybe V total, I guess, is equal to 20 over 26.67, right? Just add the 2, times V total. And now we can express V total in terms of V in. And once again, we can do voltage division there because we have 2 other resistors in series. So what we can say is V total is equal to 26.67 over 26.67 plus, well, I guess minus J, 1 over 2 times 10 to the negative 5W. And that would be V in. The total voltage drop across both of these is just V in. Okay, so let's plug this value into here then, and we should get an expression for V out in terms of V in. What we'll get is 20 over 26.67 times 26.67. Oh, that's nice. 26.67 minus J, 1 over 2 times 10 to the negative 5 times W times V in. So, the reason I said this was nice is these two are just going to go. Then, what we're going to need to do, we know that V out over V in should be 1 over root 2. So I can divide both sides by V in, and then we're going to get V out over V in is equal to 20 over 26.67 minus J, 1 over 2 times 10 to the 5 times W. So this should just be 1 over root 2, and when I say 1 over root 2, I mean the magnitude of V out over V in. They're going to be a bit out of phase, but we want their magnitudes to be 1 over root 2. 0.67 minus J over 2 times 10 to the 5 times W. Now, all we need to do is solve for W, which admittedly is a little bit harder than I just made that sound. What I would do in effort to be entirely cautious, as I would multiply the denominator by its complex conjugate. And I know there are shortcuts for how to solve this, but I'm just getting warmed up and I forget them, so there you go. 10 to the 5 times W, and then in my denominator, since I'm multiplying this by its complex conjugate, what I would get is just the square of the real plus the square of the imaginary. So I would get 26.67 squared plus 1 over 2 times 10 to the 5 times W squared. Okay, I'm going to need a new page for this. So what we have is 1 over root 2 equals the magnitude of 20 is 26.67 plus j, 1 over 2 times 10 to the 5 times w, or 26.67 squared is 711.29, plus 1 over 2 times 10 to the, is that 10 to the 5? No, it's supposed to be 10 to the negative 5. I had that up there. I was probably off the page, I'm sorry. That was 10 to the negative 5. So this was supposed to be 1 over 2 times 10 to the negative 5 times w all squared. Now at this point the denominator is real, so we can just factor it out. That's nice. Hang on a minute, there is an easier way to do this. Right. I'll continue this way for now. It should lead to the same answer. The other way would have been when I had this part here, since, yeah, when you want to take the magnitude of a fraction, you can just take the magnitude of the top and divide it by the magnitude of the bottom. But by the time I get here, I'm basically almost there. So, and this is a little bit more intuitive, perhaps. 1 over 711.29 plus 1 over 4 times 10 to the negative 10 times w squared, multiplied by the magnitude of this, which is just going to be equal to the 20 times the square of the real plus the square of the imaginary, which was just this bit, right? I think so. Yeah. So 711.29 plus 1 over 4 times 10 to the negative 10 times w squared. And yes, this was the long way around because these just cancel now, which is nice. Hold on a minute. That should be what happens. Oh, right. It's just supposed to be square rooted here. Okay, let's continue from there. 1 over square root 2 is equal to, so if you have the square root and you divide by the actual thing, you should get 1 over square root. So you end up with 20 over square root of 711.29 plus 1 over 4 times 10 to the negative 10 times w squared. Multiplying both sides by the denominators, so move this to the top over here and move this to the top over here and square both sides, you would end up with 711.29 plus 1 over 4 times 10 to the negative 10 times w squared is equal to 400 times 2. 400 being 20 squared. And then we're good. Subtract 800 from here, add this over here, and then we should get negative 89.71 is equal to 1 over 4 times 10 to the negative 10 times w squared. Why is w complex? Okay, I get it. This side, so since I'm subtracting to this side would be negative. I think as I progress through the evening here, that's what I'm going to be, what I'm going to do. I'm going to confuse myself with my math errors, and then pause it, and then figure out where the mistake is, and then I'll resume. So that saves you all a bit of time, and make sure I give you the right answer. So that works well. Now you can easily solve for w squared. We're just going to remove the negative from both sides, multiply both sides by 4 times 10 to the negative 10. We get 89.71 times 4 times 10 to the negative 10 is equal to 1 over w squared. And if we were to move w squared up here and move this down, like that, then you get w squared is equal to 1 over 358.88, 84 times 10 to the negative 10. W is equal to, so that would be 10 to the 10 on the top, so you get 10 to the 5 over square root of 358.84, and this is your 3 dB frequency, which is square root of 358.84, and then that times, so that's 100,000 divided by that. That is 5278.97 radians per second. All right. Let me proceed to the next one. I can write that up here as a final answer if you are so inclined. 5.278 radians per second. In the circuit below, and this is, I'm proceeding to part B now. In the circuit below, the current in and the current out are the input and output steady state sinusoidal currents, respectively. Calculate the gain of the circuit in decibels at frequencies W equals 0 and W approaches infinity. I'll give you 5 seconds to start it. All right, I hope that was helpful. So, when W is equal to 0, then you're just having DC, which means your capacitor acts like an open circuit, which means you basically just have one loop. So I would say at W equals 0, I out over I in is equal to 1, because all the current, none of the current can go this way, so it all has to go that way. It's only worth 2 marks, so I'm assuming you don't need to show much work for this. And then as W approaches infinity, then suddenly the current has 2 options. It can either go this way or this way, and the capacitor acts like a short circuit. Then the circuit resembles so you have that I in, and then you've got at 25 one resistor here, you got a resistor here, and you've got a resistor there. This is 20, this is 25, and this is 10. I know there is a current division formula, but what I would do in this case is say, I might do loop analysis. So I would do one loop there, and one loop there, and I would say this is I1, this is I2. I would say that, oh yeah, that's a problem. Can't really do loop analysis with the, so I'm going to do KVL then. Actually, probably could. No. You'd have to use a supernode, which is basically just the outside loop. Which isn't a terrible idea. Huh. Okay. Let's look at the current. This probably isn't the most intuitive way to do this, but let's look at the current going around the outside of the loop. In this case, we have that V loop needs to be equal to 0. But V loop is equal to your current that you have on the outside multiplied. So we'll say that the voltage here is positive, and then the voltage the other way is negative. So it's I times 25 ohms. So yeah, we'll call the current going this way I, and then plus I minus I in times, and that's the current going down, times 10 ohms is equal to 0. Yeah, because whatever current you had here, you lost I in, and then you're continuing through the 10 ohms. So that works well. And then all we need to do is should be able to move this to the other side, so you get I times 25 ohms is equal to negative I minus I in times 10 ohms. And then you can divide both sides by 25 ohms and I minus I in. So then you get I over I minus I in, is equal to negative 10 over 25, which is equal to, should be negative 0.4. So what does this say? This says that the current going this way now is equal to negative 0.4 times I, where this is I. Okay. So if you were to do KVL, you would say that I is coming this way, and then after this I get negative 0.4 I. So which means that basically it's 0.4 I going the other way. So this has to be 1.4 I. And then if you wanted to do, so this is I out is 0.4 I. and then I in is 1.4I. So I out over I in as W approaches infinity is equal to 0.4 over 1.4. And then that is equal to 0.28, 0.29. 2/7. All right, that is part B. I realized the fact that you probably... That was probably too creative an approach for too simple a problem, only worth 2 marks. Anyway, I hope you did it yourself and you got the same answer, or follow along to the way I did it. I can show you where my thinking goes. That's about all I can do. This problem C is an interesting one. In the circuit below, the op-amp is ideal, and the current source, this is your current source, I in, which is given by 4 milliamps times the Heaviside function of T, where the Heaviside function of T is the unit step function. It turns to 1 at T equals 0. In addition, the initial voltage on the capacitor is VC is equal to 1 volt. Calculate the voltage V out at T is equal to 150 microseconds. Okay, I will give you a few seconds to think this one over. Okay, yeah, this one, this was an interesting problem. So, you know that there's negative feedback on the op-amp. So, the op-amp will always have a voltage of 0, basically. Which means you can't get any current here. This voltage has to be 0. Right? Right. Yes, because this voltage is grounded. So this has to be 0. So you can't get any current through here. So all of the current going through this current source has to have come from the capacitor. Now, you can turn back to your formula for voltage through the capacitor, which is C dV of T by dt. Now, my argument would be that as you steal current from the positive end of the capacitor, your voltage across the capacitor is going to go into negative territory, right? So like as you steal a bunch of positive charges, this is going to get more negatively charged. And so your VC is actually going to go negative. So it starts at 1 and goes down from there. So I might say that I in is equal to negative C dV of T by dt. This is given as 4 milliamperes. The C is given as 5 microfarads. That's nice. dV of T by dt. And so what are you looking for? You're looking at T equals 150 microseconds. And you're looking for the V out, which is basically the voltage on the other side of the capacitor. You know that the voltage on this side is always going to be 0, right? So it's the voltage on this side that's going to have to go down. Yeah. Am I doing that right? Yes. So the voltage of the capacitor goes down. However, that means that this side becomes more negative and this side becomes more positive. So effectively what's happening is your voltage here goes up. Sorry, you probably can't see that. This side acquires a negative voltage because it's the positive charges are being stolen by this current. This acquires a positive charge, which means that there's an electric field going this way. And that means that this has a positive voltage, so the voltage here will become increasingly positive, basically. In fact, I could say the voltage here was equal to negative VC. Right? Because this side is 0, and this is the negative of V of C. Okay. And then this is VC of t. So let's solve for VC of t, and then we can easily solve for V out. You could move negative 5 times 10 to the negative 6 farads over to the other side, and you get negative 4 over 5, and these units are in milliamperes per microfarad, is equal to dVc of t by dt. This has units. Okay, so all right. 1 farad is so Q of t equals CV of t. So 1 farad is equal to 1 coulomb per volt. So this has negative 4 over 5. And a coulomb is an ampere second. So we have 10 to the negative 3 amperes over 10 to the negative 6 ampere seconds per volt is equal to dVc of t by dt. And then if we divide these, you get negative 4 over 5 times 10 to the 3. And this would give you volts per second is equal to dVc of t by dt. And then all you gotta do is integrate both sides. You get Vc of t is equal to negative 800, and then your seconds are going to go, which is nice. You're going to get volts multiplied by t plus c, where t is in seconds. And then you can say, I'm going to go over here, I'm going to say V is equal to negative Vc. Sorry, V of t, I guess, is equal to negative Vc of t. V of t is equal to, oh, right. Also, the initial Vc is 1. So this C is just going to become 1. Right? You plug in 0 for here. Boom. So V of t is equal to negative 800 volts plus 1 volt. Sorry, volts times time plus 1 volt. So we want V at 150 microseconds, and that's going to be 800 volts times 150 microseconds plus, sorry, minus, very important, minus 1 volt. V at 150 microseconds is equal to, I guess I should have left that in there, volts per second. And that becomes, so it's 800 times 150 times 10 to the power of negative 6. Okay, so your capacitor gains 0.12 volts in that time, but your initial, no, we're good. Your initial voltage was negative 1 volt. So your final voltage should be negative 0.88 volts. Okay. The next equation involves a diode. I believe Professor Wilson mentioned in class that diodes were not going to be on the final. However, I looked ahead and there are 2 diode questions on this exam, and this one is definitely the harder of the 2. So I am going to skip this one for now, and I will do the next one, just in case. All right, let us continue. Problem 2. In the amplifier below, the op-amp is ideal. Derive the transfer function of the amplifier V out of j omega divided by V in j omega. Okay. If you are comfortable with me doing so, I will represent j omega as S. Professor Wilson did that in his lectures. To be honest, when I first saw it, I got a little bit lost, but I think the exposure is good. If you ever get confused about what S is, just plug in j omega and hopefully that will sort things out. So what I can do for this is I'm going to leave this up here a little bit. Actually, I could zoom out a little bit because I need 2 pieces of paper now. So there. Hopefully you can see both papers decently well. I'll start up here. Whoa, okay. I'll start up here. And that'll be A. And we need the transfer function. So, I'm going to bring this back, and what we need to do is we need to think about how we're going to have an expression for V out in terms of V in. We know that no current goes into the op-amp because the op-amp is ideal. And we know there's negative feedback, so we know that the difference between these 2 terminals, the voltage difference is 0, which means that this voltage has to be 0. And I could make the argument right away that you immediately know, you can immediately derive an expression for the current going through the capacitor based on you have the voltage difference. Yeah. If you know the current going through the capacitor, then you can immediately tell me how much current is going through the resistor, which gives you V out. So that's the approach I'm going to try to take. All right. The interesting part is we never assume V in is a sinusoid. We never told that. But I'm going to assume that just because, well, A, makes the calculations a lot easier, and B, your V out, they say your V out is in terms of j omega. So I'm going to assume that V in has an omega to it. Which means that you can represent, so for the capacitor, what we have is I of t is equal to C dV of t by dt. And we have the voltage across the capacitor. That is just, and we'll represent this terminal as positive, this terminal as negative. We have that is equal to V in minus 0, or just V in. And then I'm going to further assume that V in is equal to V in total, like a DC maximum times cosine of omega t, which we can just represent as V in times e to the j omega t. Okay, so what we can do from there is take the derivative. So we get I of t is equal to c times j omega Oh, right. I want to represent that as S. I'll do that in the next step. Times Vn times e to the j omega t. And then I of t is equal to c times s times Vn times e to the power of st. Okay, we have c. I'll just leave it like that for now, but keep in mind that that's a given constant. And from this current, we can find an expression for the voltage across this resistor. So, V out minus 0, which is the two terminals of the resistor, is equal to I'm going to say negative I of t, right? Because if I of t was the current through the capacitor going this way, then negative I of t is the current across the resistor going this way, right? All the current has to go through here. We can represent this as negative I of t, and that way we can represent V out minus V0 as I times R. So that current is negative I of t, and then our resistor is just 8,000 ohms. Easy. V out is equal to negative C S, S being j omega, times Vn times e to the power of st times 8,000. If we want an expression for V out over Vn, I would say that Vn is right here, right? It's the maximum of Vn multiplied by e to the power of j omega t. So what we can do is V out is equal to negative C S Vn times 8,000. And then we can divide this by Vn, and we get V out, or divided by Vn, is equal to negative C S times 8,000. And that is your transfer function. That was only one mark. Wow, okay. Sketch a Bode magnitude plot. We didn't do a lot of those. You probably can't see very much. I'm going to move this over. Sketch a Bode magnitude plot of the transfer function from part A. Make sure you indicate the following on your sketch. The gain for any segments of the plot that are constant with frequency. The slope in decibels per decade of any segments that have non-zero slope. The values of all pole, zero, and unity gain frequencies. And again, we didn't really do pole frequencies. I'm going to change this to negative 3 dB frequencies because we did a lot more of those. Okay, so I will move this over here, and hopefully you can still see both pages. Not really. Let's move that. Close enough. So, keep in mind that we need a Bode magnitude plot. And the interesting thing about a Bode magnitude plot is it doesn't just plot the gain with respect to the frequency. It takes the log of the frequency and also takes the log of the gain. And then it just plots them. So if you wanted to go back to your formula here, this is the gain. If you wanted the log of it, that would be, so C, I guess I could plug that in. That's 0.4 microfarads. So we could say, I guess A is the magnitude of the gain, isn't it? So I shouldn't have the negative there. Bye-bye. So it's log 10 of C, log 10 of S, log 10 of 8,000, and then you add them all by logarithm rules. I guess I could have combined these. Yeah, I'll do that after. So log 10 of A is equal to log 10 of S times log 10 of 8,000 times C, which is 0.4, or 0.4 times 10 to the negative 6. 10 to the negative 6. Then log 10 of A is equal to log 10 of S. Oops, got an addition there. All right. So this is 4 times 10 to the negative 7, if that's helpful. It kind of is. Log 10 of 32 plus log 10 of 10 to the negative 4. So this is 10 to the negative 7. This is 8 times 10 to the 3. I combine the exponents, you get 10 to the negative 4, and then you have 8 times 4. 32. Okay. All right. So it's just a line. This is negative 4, by the way. So log 10 of A is equal to log 10 of S plus, I guess I can just do it. Log 10 of 32 is 1.5 or so. And this is, yeah, negative 4. So this combines to make 2.5. Negative 2.5, sorry. Log 10 of A is equal to log 10 of S plus minus 2.5. Alright, so it starts here at negative 2.5, and then you get that. And so, it asked for the gain of any segments of the plot which are constant with frequency. That would mean a horizontal line. I don't see any horizontal lines, so you don't need to worry about that. The slope in decibels per decade of any segments that have non-zero slope. So this should be slope is equal to 1. The values of all negative 3 dB, 0 in unity gain frequencies. So, can't really rely on the magnitude plot for this. But as S goes right. So a 0, and I'm still getting used to these boat plots, so I'm sorry, bear with me. Log 10 of A, if you were looking for a place that had 0 gain, you would want to look for log 10 of A to be negative infinity, because log of 10 of 0 is negative infinity. And this line continues. So this approaches negative infinity when log 10 of S is negative infinity. And log 10 of S is negative infinity when S is equal to 0. So, your 0 gain point is when j omega is equal to 0, or with DC. And what happens when you have DC is no current's getting through that capacitor. So, of course, the voltage across this resistor is going to be 0. So, it checks out. What else do you need? You need a negative, let's do the unity gain first. Unity gain 1 is easy. Unity gain. So unity gain is when A is 1. So log 10 of 1 is 0. So you're wondering what frequency gives you a gain of 0. And that occurs at the x-axis here, which would be log 10 of S is equal to this was negative 2.5, so this would be 2.5, which means that S is equal to 10 to the power of 2.5, which is 320 or so. Yeah, that checks out. So your amplifier here has the voltage V out equal to V in, equal the magnitude of the two anyway, is equal when the frequency of V in is 320 radians per second. Then it also looks for the negative 3 dB frequency. Actually, that doesn't apply in this case. I don't think, because yeah, I wouldn't worry too much about either of these. Normally, with a negative 3 dB frequency, you need to know what the maximum transfer is. But there is no maximum transfer, right? If you increase V in, you're going to get pretty much as much current as you want through this capacitor, which means V out. This could be astronomically large gain. So don't worry about a negative 3 dB frequency in this particular case. Sketch a phase plot. Okay. Sketch a Baudouin phase plot of the transfer function from part A. Make sure you indicate the following on your sketch: the phase in degrees for any segments of the plot that are constant with frequency, the slope in degrees per decade of any segments that have non-zero slope, and the values of all, well, okay, we've already done that. So I'm skipping that one. Okay. So, steal a paper here. I'm going to move this one over. So what we had for the equation of our gain was this one. V out over V in is equal to C times S times 8,000, which we found was equivalent to A is equal to J omega times 8,000 times 0.4 times 10 to the negative 6, which would be 320 times 10 to the negative 6. Nope, 3,200 times 10 to the negative 6. 32 times 10 to the negative 4. Right. So, this is the equation for our gain. Not just the magnitude, but also the phase. I guess there was a negative here. I should include that. As you can see, the V out over V in is always 90 degrees apart. And the reasoning for that is that your capacitor will always output a current that's 90 degrees apart from the voltage it sees. Because I of t is equal to C dV of t by dt, which is C j omega V of t. So your voltage change across here, which is equal to the current, proportional to the current anyway, is always going to be 90 degrees away from your input voltage. So your both phase plot, pretty easy. It just looks like where this is negative 90 degrees, or I guess negative pi by 2. And I get that from the fact that your gain has phase negative pi by 2. Yeah. There's no places that have non-zero slope, so that's easy. Yeah, so I'll draw a line here, and we'll go to the next one. Determine V out of t when V in of t is equal to 2 times sine of 500t volts. So I would argue that this equation would be most helpful for us. So I will rewrite that here and then proceed from there. We get V out is equal to negative CS times 8,000 Vn. If you'd like to see the question while I work, I'll try to, I can move this over. I'll try to set it up like that. Okay. V out is equal to negative 0.4 times 10 to the negative 6. S is j omega. 8,000 times Vn. V out is equal to negative 3,200 times 10 to the negative 6 times j, and notice our omega is 500. So we can plug that in, and then we could represent this as 2 times sine of 500t is e to the j omega t plus, is it plus? No, I think it's minus. Minus pi by 2. So what this does is this just sets the sine wave back by, sets the sinusoid back by 90 degrees. So instead of starting at 1, it's going to start at 0. Basically saying the same thing as sine is equal to a cosine phase shifted by pi by 2. V out is equal to negative 3,200 times 10 to the negative 6, 500j, 2 times e to the j 500t minus pi by 2. That's a lot of terms. Okay, so this is 1,000. That's nice. That's 10 to the 3, so this can become 10 to the negative 3. So we get V out is equal to negative 3.2, or 3.2 times 10 to the 3 times 10 to the negative 3. J e to the j 500t minus pi by 2. And then I would make the argument that j is equal to e to the power of pi by 2. E to the power of, oh, yeah, e to the power of j pi by 2. So V out is equal to negative 3.2 times e to the power of j pi by 2 times e to the power of j 500t times e to the power of negative j pi by 2. And then these cancel. So you get V out is equal to negative 3.2 times e to the power of j 500t. And so what this says is that when you input a sign here, you would end up on this side with a cosine, right? Because when it's in phase, e to the j 500t is the same as cosine of 500t. Okay, let me put this back for the next question. Show where one resistor R, set to an appropriate value, could be added to the amplifier circuit such that the voltage gain magnitude V out over Vn at DC is 6 volts per volt. Also indicate the value of the resistor R. So before I begin, I'm going to give you a hint. At DC, remember, the capacitor works like an open circuit. So we're going to need a way to make sure that this resistor is seeing at least some current. Alright, I will give you 5 seconds while I go get a drink from my clear water bottle. Okay. These honor statements during COVID went crazy. Okay, sorry. I need the paper. Can you see both of those? Pretty well. Not bad. All right. Determine V out of T when V in of T. No, that's not the one we're doing. Sorry, my bad. I have brought this for the occasion. This is the same circuit as before, but we need to add something this time, such that the DC voltage is 6 volts per volt. And so what I would recommend is, since we have DC, this capacitor is going to look like a open circuit, so we can just treat this like a regular inverting amplifier and throw in an input resistance like that. Yeah. So you know that this voltage, again, needs to be 0. And you want, basically, you're going to get the same current through both of these. And you want it to lose 6 times more voltage here than you want it to lose here. So the resistance of this one needs to be 1/6 of the resistance of this one. So this would be 8 over 6 kilovolts. And, sorry, not kilovolts. Kiloohms. And that would be what I would add to the circuit. Also indicate, yeah. Okay, let's read the next one. Let input signal V in of T behave according to the waveform in the graph below. Sketch a graph of the load current, and this is your load here. IL from 0 to 8 milliseconds. Be sure to quantify the current amplitudes and important time points on your graph. Note in this part, consider the original circuit in the figure at the top of the page. Yeah, okay. You can see that your V in is not changing with time for the first 4 milliseconds. I'm going to need paper for this. So let me use this one. So we'll make this graph be IL, and we'll make this one be T. And we'll call this 4, this one's 6, this one's 8. So my current is DC. Sorry, not current. My voltage is DC, not changing, for the first 4 milliseconds, which means that no current gets through the capacitor. So this voltage is going to end up being 0. You're not going to get any current. So we can just draw a line like that. Then in the second half, we get a decreasing voltage in Vn, which means that this, of course, the voltage across the capacitor will be decreasing as well, which means current is going to be flowing this way. Yes. If the voltage in the capacitor is built up by putting charges from the voltage source there, then the voltage can be taken down again by removing those charges. So you would get a positive current flow going this way, which means current would flow this way across the 8 kilo ohm resistor as well. And Yes. So your voltage, V out, in this case, would be, okay, so this slope here, so this is 2 milliseconds, or 1/500 of a second. And your change in voltage is 3 volts. Which means that your rate of change is 1500 volts per second. If you were to plug this into the capacitor equation, you would see that I don't have it written for some reason. I'm going to write it in the new one. I don't want to cover that up. Okay, let's move like this. Hopefully you can see that. Pretty well. Okay. I can zoom out a little bit. There you go. This means that I of t across the capacitor is equal to C dV of t by dt, and we know that that was 1500 volts per second, and this was 0.4 microfarads. If you were to plug all this in, you would see this 15 times 4 would be 60, so basically 6, and this would be milliamperes, because you get a, would it be? No, it would be 0.6, 0.6, because, yes, multiplying this by 0.4 would give you 600, and then you would want to divide it by 1,000 to give you 0.6 amperes, and then divide it by 1,000 again because it's microfarads, and that would give you 0.6 milliamperes. Okay. Which means that the voltage drop across the resistor would be 0.6 times 8, which would give you 4.8 volts. This means that V out is equal to 4.8 volts. And then you're sending that across a 5 kilo ohm resistor. So if you wanted the current, you would divide 4.8 divided by 5, and that would give you 0.96 milliamperes. So this would take a jump up and plateau off like this, and that would be 0.96 milliamperes. Now, after that, your voltage change goes from discharging the capacitor at a rate of 1500 volts per second to suddenly charging the capacitor again at a rate of 1500 volts per second. So I would argue that your current should just be the opposite, and therefore your voltage here would be negative 4.8, which means that, which means that current goes this way. Yes. And so your IL is negative, but it would be the same magnitude. So you'd get negative 0.96 milliamperes, and your current would look like that. All right, that was question 2. Wow, okay. Problem 3. In the circuit below, this is the diode one. All right. In the circuit below, the diode behaves according to the constant 0.7 volt drop model. Current source I of t provides a sinusoid as shown in the graph, and resistor R1 is equal to 3 kilo ohms and R2 is equal to 2 kilo ohms. Sketch the output voltage VO of t of the circuit over one period of the input sinusoid. In your sketch, be sure to quantify the coordinates of the important points on the graph, example, times when the diode turns on or off, amplitude of the output voltage at t at these times, and the value of the output voltage of t at any time when V output of t is constant, stuff like that. Okay. I will give you 5 minutes to contemplate this problem and think about how you would write out a solution, and then I will proceed with my own answer. Alrighty. That's my best mic impression. Okay. Um, so, I would make the argument that your diode can either be on or off. I know, brilliant. Okay. So when your voltage output is, well, let's first assume it's off. And then when your voltage output becomes greater than 0.7, then suddenly we're going to have to I guess the word is account for the fact that it's on. I don't know what I was. Prepare for the fact that it's on. But for now, we can start by imagining it's off. And so, in fact, if the current is negative, then your current needs to return, and it's not returning to the diode. So you can pretty well assume that VO of t, that the diode is going to be off for the negative half here. So we could just straight up draw that in. That just looks like that. Nice. This is t in seconds, being 2 and 4. And this is VO of t. All right. And your maximum. Your maximum, oh, yeah. Your maximum occurs when I of t is equal to negative 2 milliamperes. Negative 2 milliamperes multiplied by 2 kilo ohms gives you a minimum voltage of negative 4 volts. Now, you can imagine that the sinusoid would continue to behave this way until VO of t, even on the positive side, until VO of t reached 0.7 volts. Then suddenly the current has two different ways to go. Yes. So, at this point, I think I'm going to start needing some equations. And that would be my recommendation for any problem on the exam. If you're not really sure where to go next, spam equations and see if you can get something going. So what we have is VO of t is equal to I of t. So for VO of t, hang on. Okay. When is VO of t greater than 0.7? It's greater than 0.7 when the current is greater than 0.35 milliamps. Because I is equal to V over R. This is 0.7. This is 2,000. So you get 3.5 times 10 to the negative 3. And that yeah. And they're wondering when that occurs time-wise. So, we know that I is equal to 2 sine of pi over 2t, because at t is equal to 2, we're at pi, radians wise, and then our amplitude is 2. And we're wondering when this is equal to 3.5, hang on. No way. Oh, sorry. Carried a 0 in the wrong spot. So this is supposed to be 0.7, and then we're dividing by 2 kiloohms. So you get 0.35. That makes a lot more sense. Okay. 0.35 is equal to 2 sine of pi over 2t. And then we're going to divide by 2. We get 0.175 is equal to sine pi over 2t. Sine negative 1, 0.175. Okay, calculator time. Sine negative 1, 0.175. Oh. I just remember Dita saying for small angles, sine of x is equal to x. Yeah, that's where that comes in. Times 2 divided by pi. And that's going to give you 0.112. So, at t is equal to 0.112. And I guess 2 minus 0.112, which would be 1.888. VO of t is equal to 0.7 volts. Then, at these times, VO of t is equal to, I'm going to call this I1, and I'm going to call this I2. Then what we have is for VO of t greater than 0.7 volts, VO of t is equal to I1 of t times 2000. And then VO of t is also equal to, so this voltage is 0.7, and this is R1 times I2. So VO of t in total is going to be equal to 0.7 plus I2 of t times 3000. Sorry, covering up the page here. And then we need one other equation, I believe, and that would come from the fact that I1 of t plus I2 of t is going to be equal to I of t. And then what we can do is we can make an expression for VO of t with respect to I of t, because we would have VO of t over 2000 plus VO of t minus 0.7 over 3000, and that's going to be equal to I of t. A little bit of rearranging to do. So what we're going to say is VO of t times 1 over 2000 plus 1 over 3000 is equal to I of t plus 0.7 over 3000. And from there, it's not too bad. I'll just do it. VO of t multiply this by 3 and this by 2. You should end up with over 6,000, and this would be 3, this would be 2, so you get 5 over 6,000. It's equal to I of t plus 0.7 over 3,000. Really? Oh. All right. 0.7 divided by 3,000, that gives you, 2.3333, 2.333 times 10 to the negative 4, multiply both by 6,000, divide by 5, VO of t is equal to 6,000 over 5, I of t, plus some constant anyway. Won't make too much importance, but it's going to be 14 over 5? Yeah. Times, oh, 1, so it's 1.4 over 5. Okay, so this makes sense. So originally when we had a amplitude of 4 for an input amplitude of 2, yeah, I'm just going to plug in, we have an equation for I of t, so I can express this right in terms of t. I of t is equal to 2 sine of pi by 2t, so it's going to be 12,000 over 5. Oh, yeah, but that's in milliamps. So 12 over 5 then. 12 over 5. 12 over 5 sine pi over 2t plus 1.4 over 5. So what does this say? This says that your maximum VO of t is less than what this sinusoid had suggested, right? The maximum here would have been 4, but with this new sinusoid, your maximum is only 2.4. Which makes sense, because now the current has 2 different ways to go. So the voltage required to send that current is a little bit less. So your thing is going to look a little bit more clamped off like that. We've seen that in the labs. All right, let me continue. So that is problem, and then we can put in the maximum here. That would be, so 12 over 5 plus 1.4 over 5, so really? 13.4 over 5 volts. 13.4 divided by 5? 2.68 volts would be your, according to this diode model anyway, would be our maximum voltage. All right, problem 4. In the circuit below, supply voltage VDD is equal to 5 volts. Resistors R1 is 400 ohms and R2 is 600 ohms. And DC current source IB, I hope you can see this, is equal to 2 milliamperes. In addition, transistors M1 and M2 are identical. This looks like a PMOS. Oh no. That's okay. That's okay. That's okay. Is it a PMOS? Yeah. Unless... yeah, it's a PMOS. It's a PMOS. That's okay. And DC current source IB is equal to 2 milliamperes. In addition, transistors M1 and M2 are identical, with Kn is equal to the product of those two. So there's no way he gives you that. So Kn is equal to 600 microamperes per volt squared. Threshold voltage is negative? What the? Oh, right, because they're PMOS, so of course the threshold voltage is negative. Ooh. And lambda equal to 0. Okay, they mercied us. All right. Yeah, let's roll with it. Determine the drain current of M1. All right. Well, I'm going to need a few seconds to think about this, so I give you a few seconds of your own time. Okay. They kind of walk you through this. This is nice. So your IB is guaranteed to be 2 milliamperes. Oh, all right. A little bit tougher than I thought it was. R1 is $400. This current is, of course, 0, right? Because you're never going to get any current out of the gate. Then so we should make an expression for the current through, drain current. So in a PMOS, this is the gate, and current flows from source to drain. Yes. I'm not sure about that. I'm gonna look that up.